Hi, in this video we will learn how to express the area under the graph of a positive continuous function as limit of a sum. We will use the right endpoint approximation and you will see the details of what is going on for this method. Throughout this video we are assuming that the f is a positive and continuous function. Well, it doesn't need to be everywhere. We are just restricting ourselves on an interval. So interval A to B. Well, if you look at the graph of such a function, well, typical function will have a graph of this form, continuous, positive. Now, the question is, what is the area of the region under the graph of this function? So this shaded area, what is the area with this shaded region? What is the area of that? Well, it is not a regular shape, and I cannot give you just one formula because it really depends on what is f. But what we can do, we can use some approximation, and limit of the approximation will be the area. So we will use approximation using rectangles. How does this work? Okay, so first thing is that we will chop the interval AB into equal subintervals. Well, let me just do it in 3 cases. Well, I chopped it in three subintervals. Well, then we have 1, 2, 3 subintervals. The right endpoint of each subinterval is, so the first one is going to be called x1, the second one is going to be x2, the third one, which is b, is x3. Yes? Now, I will make a rectangle whose width is this subinterval a to x1. What I do is just draw a line from the right end point of that subinterval and stop when I hit to the graph of the function. Then form the rectangle using that. For the second rectangle, I'll do the same thing. And for the third one, I'll do the same thing. Now, these rectangles, well, we can compute their areas. Why? Because you see, I have the width, which is, so I divided AB into 3 equal subintervals. So the length of each of these widths are going to be b minus a over 3. And what about the height in this case, or the length? Well, you see, it is the value of the function. I said draw a straight line, vertical line from the right end point until you hit the graph. So this piece here is nothing but f of x1. Here, this is f of x2, and this guy is f of x3. Then when you have those ones, you just multiply those and find area of each rectangle, add them, and you have an approximation using 3 rectangles. 3 rectangles by right end points. So the sum of those ones we would write as R3, R standing for right, 3 number of the rectangles. Well, you will say, stop here. What you found is not definitely the area, the region we were looking for. this is just some strange thing. Yes, if you look at R3, you're right. We don't compute a good number. But if I increase the number of subintervals, so increase the number of subintervals. So what I mean is that for any n, we can repeat this thing. So r equal to 3, you can do r3. N equal to 3, we can do 3 rectangles. N equal to 4, we can do 4 rectangles, 5 rectangles, and in general Rn. Then you find the limit of that as n goes to infinity. This will be the number which will get closer and closer to the area of the region under the graph. And well, that's the general strategy we have here. So we have to go ahead, find all these numbers, and get a formula, and then find the limit. Okay, so in details, one need to do these 4 steps. Step 1 is that divide the interval AB into n equal subintervals. So AB is there. You divide it into n pieces, n equal pieces. The length of each subinterval is equal to the length of the total interval, which is b minus a, over n. Well, we have a notation for this. We call this delta x. So here is the length of this one is delta x, delta x, delta x, and so on. Then we also need to find what is the right endpoint of ith rectangle. So here the first not rectangle, subinterval. The first subinterval is this. I'll call this one x1, the right endpoint. Then x2, x3, and so on. Well, in general, for ith, I will put xi. And what is the formula for that? You see, xi has I subinterval before we get to that point. So if you want to see the total length of subintervals before x3 is I times delta x. And well, we know that the first subinterval starts from a, so I need to add a to that. In other words, this formula, you can write it as this: I b minus a over n. Why do I need this? Well, because I will use that and find the area of the ith rectangle. Well, what is ith rectangle? So we have xi here on the right end. And then the height of this guy is f at that point, and then you have this rectangle here. The area of this, so area of ith rectangle is equal to x. So, well, let me just make the width is delta x, and the height is f of xi. So then the area will be width times length or height here. this will be what we have. Very nice. This is just area of one rectangle, but our approximation will give us n rectangles. So find the sum of areas of rectangles. So the first rectangle has area delta xf of x1. The second one has delta xf of x2. And this will go up to the nth. Well, this will be sum of areas of rectangles. And as I mentioned before, we will denote this guy by Rn. R standing for the right endpoint, and n standing for the number of subintervals. Well, I can use the sigma notation to denote this thing. This is delta x f of xi. I goes from 1 to n. So we'll go from 1 to n. Well, now that you have that, step 4 is find the limit. Find the limit means that you increase the number of the subintervals or rectangles as large as you can. So this will be limit of this guy, I going from 1 to n, as n goes to infinity. This is going to be area under the graph, the region under the graph of f. So we need to form that. Well, I can put a little bit more details there. For example, n goes infinity sum. I know that the formula for delta x is b minus a over n. And I know the formula for xi is a plus I b minus a over n. And that will give you the sum. If you can find the sum as it is, then you will be able to evaluate or find the limit as n goes to infinity. Well, in the other videos, we will do some examples for this. Please make sure that you watch those ones because this was very theoretical and everything was for general thing, but you will see in the examples that everything will fit in this general picture nicely.